Unit 6, Section 3, Integration of exponential and logarithmic functions. Session objectives. By the end of this session, the student will be able to 1. Integrate functions involving exponential functions. 2. Integrate functions involving logarithmic functions. Integration of exponential and logarithmic functions. We have seen that in differentiation, if a function f of x is given as e power x, and we find the first derivative of f of x, then it gives the first derivative of f of x to be e exponent x. Likewise, if the function f of x is given as a exponent x, if we differentiate that, it gives a exponent x ln x. And since integration is the reverse of differentiation, when we integrate e power x dx, it gives e power x plus c. If we integrate a power x dx, it gives a power x over ln a plus c. In the situations where the exponent of e and the exponent of a are functions of x or any other variable, then we resort to integration by substitution. That is by letting u equals kx and differentiating u with respect to x, du over dx gives k, and making the x the subject, we have du over k. This is because the exponent of e is kx and that of a is kx. The integral of e exponent kx dx is equal to the integral e power u, since our kx is u. Then the dx should be written in terms of du. So we have du over k. Now 1 over k is a constant, so we bring it out to have 1 over k, the integral e power u du. Now when we integrate e power u, it gives e power u, multiplying 1 over k, then plus c. But we know our u to be kx, so we substitute kx in place of u. Hence, we have the integral e exponent kx dx to be 1 over k e exponent kx plus c. Likewise, if we are given the integral a exponent kx dx, it gives a exponent kx over k ln a plus c. Example. Evaluate the following integrals. A. The integral 14 e power 7x dx. B. The integral 7 exponent 2x plus 3 dx. Now in the first case, to find the integral, we let our u to be 7x, which implies that if we differentiate u with respect to x, we have du over dx to be 7. And making the x the subject, we have the x to be du over 7. Now replacing 7x and dx with u and du over 7 respectively, then we have the integral 14 e power u multiplying du over 7 plus c. Now, if this is multiplied out, 7 divides 14, 2. and that 2 is a constant. So the 2 is factored out. So, or we bring the 2 out so that we have 2 the integral e exponent u du plus c. Now, if we integrate e power u, it gives e power u. Then we multiply it by 2, and hence we have 2e exponent u plus c. But we know our u to be 7x, and hence the integral of 14e exponent 7x dx is equal to 2e power 7x plus c. B, we let u to be 2x plus 3, which implies that our du over dx is equal to 2. And making the x the subject, we have du over 2. Now replacing the x and 2x plus 3 with u and du respectively, we have the integral 7 exponent 2x plus 3 dx equals the integral 7 exponent u multiplying du over 2 by plus c. Now 1 over 2 is a constant. So we bring 1 over 2 out, then the integral 7 exponent u du plus c. Now when we integrate 7 exponent u, it gives 7 exponent u over ln u. Then we multiply it by half to obtain 7 exponent u over 2 ln 7 plus c. But we know our u to be 2x plus 3. So we replace u with 2x plus 3. Therefore, the integral 7 exponent 2x plus 3 dx is equal to 7 exponent 2x plus 3 all over 2 ln 7 plus c. Integration of logarithmic functions. We saw in differentiation that if ln x is differentiated, it gives 1 over x. However, to integrate ln x requires a technique like integration by parts, which is so technical, and hence a formula is stated as below. The integral of ln x dx gives x ln x minus x plus c. And since x is common, we factor it out. And then we have x into braces ln x minus 1 plus c. Example, evaluate the following integrals. A, the integral ln 2x dx. B, the integral ln into braces 2x minus 5 dx. C, the integral log x base 10 dx. Solution A, to integrate ln 2x dx, we use laws of logarithm to rewrite ln 2x since 2x is a product. And by that law, if we are multiplying, we add. Hence, ln 2x is expressed as ln 2 plus ln x, which implies that the integral ln 2x dx is equal to the integral ln 2 dx plus the integral ln x dx. Now, if we integrate ln 2 dx, it gives x ln 2. And by using the definition stated earlier on, that the integral ln x dx gives x into braces ln x minus 1 plus c. B, to integrate ln into braces 2 x minus 5 dx, we use the integration by substitution by letting u equals 2x minus 5 and differentiating u with respect to x and making the x the subject. We have the x to be du over 2. This implies that our integral ln into braces 2x minus 5 dx is equal to the integral ln u times du over 2. Now we have half as a constant, so we bring it out. Then we have half the integral ln u du. Now ln u du is the same as ln x dx. So therefore, we have 1 over 2 u into braces ln u minus 1, then plus c. Now we replace u with 2x minus 5, and that gives the integral ln into braces 2x minus 5 dx to be equal to half into square brackets, then braces 2x minus 5, another braces ln 2x minus 5 minus 1 plus c. C. To integrate log x base 10 dx, we change this common log into a natural log by the use of change of base. We know to change a base in log, if log a base b is given and we are changing from base b, let's say to c, then we have log a base c divided by log b base c, meaning we have changed from base b to c. So to change from a common log to natural log, log x base 10 now gives ln x over ln 10, which implies that our integral log x base 10 dx is now equals to the integral ln x over ln 10 dx. But the ln 10 is a constant, so therefore 1 over ln 10 should be brought out. So we have 1 over ln 10 multiplying the integral ln x dx. But we saw earlier on that ln x dx is x into braces ln x minus 1 plus c. So we multiply the constant 1 over ln 10 by into square bracket x into braces ln x minus 1 and plus c.